Hey everyone, this is Rita Davda. In today's chemistry lecture, we're going to be talking about intermolecular forces. In our last lecture, we talked about the states of matter, and I mentioned how intermolecular forces play a role. This week, we're going to talk about those intermolecular forces, or the attractive forces that exist between molecules. Intermolecular forces play a large role in chemistry, and can connect to many other topics. They can explain why reactions occur the way they do, or how to draw a molecule. The attractive forces between molecules is the way that molecules interact, and whether or not the forces can be overcome during a reaction or a phase change depends on their strength. There are three main types of intermolecular forces that chemists look at, and that we're going to be going over today. In order of increasing strength, they are called London dispersion forces, dipole-dipole bonds, and hydrogen bonds. Lesson guideline. Intermolecular forces play an important role in understanding the relationships between different atoms and how they interact with each other. The topics we're going to cover today are an introduction to polarity, London dispersion forces, dipole-dipole interactions, hydrogen bonds, and then a summary with some practice problems at the end. Previous knowledge, polarity. To understand how these intermolecular forces work, you'll need to understand the concept of polarity. Polarity in a molecule occurs when there is a difference in electronegativity within its atoms. Electronegativity is the measure of how attracted an atom is to an electron, which is just a fancy way of saying how much an atom wants to gain an electron. When one side of a molecule has an atom that really wants an electron, and the other side has an atom that does not want an electron as strongly, the energy becomes unevenly distributed, and thus the molecule is polar. Now, just to clarify, knowing the precise nuances of polarity in molecules can be pretty advanced, so just think of it as a molecule with an uneven energy distribution in a permanent dipole bond. Polar can also refer to opposites, so think of the polar molecule as having one end positive and one end negative, similar to a battery. Understanding the concept of polarity will help you understand the differences in strength between the different types of intermolecular forces. You should also be familiar with the concept of metals and nonmetals, and just know that a metal bonded to a nonmetal is an ionic bond, and a nonmetal bonded to a nonmetal is a covalent bond. Up here at the top, you'll see an HF molecule, and this is a polar bond because of the electronegativity difference between the hydrogen and the fluorine. You can see up the top there's a positive sign and a negative, showing how it's polar and the sides are oppositely charged. London dispersion forces. London dispersion forces, or LDFs for short, are the weakest of the three intermolecular forces. By weakest, I mean that they are the easiest to overcome, so molecules with only LDFs use less energy when they react and change their states of matter, often making these processes much quicker. Now, how do the molecules interact? Random movement and collisions create temporary dipoles, which is, as we just talked about, one side positive and one side negatively charged. And these dipoles create dipoles in nearby molecules, thus allowing the molecules to attract each other. All molecules have LDFs. However, when a molecule has another type of stronger intermolecular force as well, we mainly look at that stronger force. For example, water has hydrogen bonds, dipole-dipole forces, and London dispersion forces. But we mainly consider water to only have hydrogen bonds, since they are the strongest. This is why we consider only the weakest molecules to have LDFs, since they only have that one type of intermolecular force. Molecules with LDFs are often covalent molecules, because covalent molecules are made of nonmetals, which usually have similar measures of electronegativity. Remember how the greater the electronegativity difference, the more polar and thus stronger a molecule is. As a result of this property, most covalent molecules are nonpolar and only have LDFs. At the bottom here, you can see SO3, which is a molecule with London dispersion forces. You can see the energy is evenly distributed and the molecule even looks symmetrical. Dipole-dipole interactions. Dipole-dipole forces are the second strongest type of intermolecular force. Not all molecules have these, unlike LDFs. Since they're stronger, they are harder to overcome, and thus it takes more energy to change the physical or chemical aspects of a molecule with dipole-dipole forces. How do these molecules interact? Rather than the creation of temporary dipoles and LDFs, dipole-dipole forces exist due to the creation of permanent dipoles. or oppositely charged ends of a molecule. Only polar molecules have dipole-dipole forces, as the polarity of the molecule allows for a permanent dipole to exist. An example of a molecule with dipole-dipole forces would be hydrogen cyanide, or HCN. You can see right here at the bottom there's a drawing of HCN. Notice how there's a stronger pull between the H and the C atom than between the C and the N atom. This pulls the entire molecule towards that hydrogen atom and creates a permanent dipole moment. The greater the difference in electronegativity within a molecule's atoms, the stronger the dipole-dipole forces. At the top you can see a Lewis structure for H2S, and this is another polar molecule with dipole-dipole interactions. Finally, we have hydrogen bonds. Hydrogen bonds are the strongest type of intermolecular force. They are very hard to overcome, and it takes a lot of energy to change a molecule with hydrogen bonds. How do the molecules interact? Hydrogen bonds are a special, extra strong type of dipole-dipole force. They only occur when a hydrogen atom bonds to a nitrogen, oxygen, or fluorine atom. Since hydrogen atoms are so small in comparison to N, O, and F, the forces between them are especially strong. Again, only polar molecules with an H atom bonded to a N, O, or F atom can form hydrogen bonds. Water is a great example of a hydrogen bond, which is formed between the H and O atoms. As you can see at the bottom, the structure of the water molecule looks like an H bonded to an O bonded to an H. So there are two places in which hydrogen bonding occurs. Similarly to dipole-dipole forces, the greater the difference in electronegativity, the stronger the hydrogen bond. And summary. There are three main types of intermolecular forces that chemists take a look at. All molecules have LDFs, which are the weakest forces and the easiest to overcome. Only polar molecules have dipole-dipole forces, and only hydrogen atoms bonded to nitrogen, oxygen, or fluorine can form hydrogen bonds, which are the strongest force and the hardest to overcome. Let's do some practice problems. What type of bond does H2S have? The answer would be C, dipole-dipole interactions, because it's a covalent bond that is also polar. And a challenge problem, why does it take so long for water to boil? The reason it takes water so long to boil is because boiling is a phase change from liquid to gas, and bonds must be overcome for this change to occur. Based on the structure of water, H2O, there are two instances in each molecule where an H atom bonds to an O atom, creating a hydrogen bond. Hydrogen bonds are the strongest type of intermolecular force and are the hardest to overcome. This means it takes a lot of energy, often in the form of heat, for hydrogen bonds to be overcome or broken. The more energy needed, the longer time the reaction or phase change takes to complete, and thus water takes a long time to boil. Well, that is it for this lecture. So I hope you learned something today, and please look forward to another one soon.